Welcome everyone that's come along tonight. Thanks for joining. We're very pleased tonight to have a couple of speakers to talk to the Deep Sky section of the British Astronomical Association. I'm Callum Potter, Director, as many of you will know. Joined tonight by Adam Dillamore, who is kind of between Cambridge and UCL now, and our Assistant Director, Jim Latham. So I think Adam's going to kick off the evening and talked about the evolution of the Milky Way, which is a subject which I heard him speak briefly on at the National Astronomy meeting, and I think it should be actually I learned a lot at that meeting. So my knowledge is severely out of date. So I'm very pleased that Adam was able to come along tonight and talk about this. So I'll pass you over now to Adam.
Okay, thank you very much for inviting me. So I'm Adam Dillamore. I've just finished my PhD at the Institute of Astronomy in Cambridge, and I've just started as a postdoc at UCL. So I study the Milky Way, with a focus on its dynamics and its history, which are very closely linked, as you'll see in this presentation. So I've titled the talk "An Archaeologist's Guide to the Galaxy." Obviously not a ground-based archaeologist, but a galactic archaeologist, because there are some similarities between archaeology, digging in the Earth, and galactic archaeology, digging in the galaxy. So what is galactic archaeology? Well, this is all based on the idea of hierarchical structure formation, which is a key idea in our model of cosmology. So we have a cold dark matter based cosmology, which means that we have dark matter particles which are reasonably slow. Makes up much of the matter of the universe, not moving particularly quickly. This means that the way that structure formation works, small galaxies form first, and then larger galaxies form by the merging of these smaller galaxies into larger ones, and then into galaxy clusters and so on. So this may seem reasonably intuitive, but not all cosmologies would give you this. Sometimes if you have warmer dark matter, i.e. dark matter that has a hotter temperature, that would mean you'd form larger structures first, and then they'd fragment to form smaller structures. But we are almost certainly not living in a universe like that. We live in a cold dark matter universe, which means that we have many small galaxies. The universe is dominated by light small galaxies, which merge with other galaxies like the Milky Way. So galactic archaeology is the study of these old galactic fragments which have merged with the Milky Way over its 14 billion year history. So there are various tools employed in the field of galactic archaeology. The main ones are dynamics, so looking at where stars are, how they're moving, what their orbits are like, because this preserves information about how they merged, how they arrived at their current positions, which depends on where they were born. Chemical abundances, so different stars born in different galaxies would have different chemical abundances, such as iron abundance is a main one. And stellar parameters like temperature, surface gravity, which tells you like whether it's a giant star, for example. And the most basic division we can do is divide stars up into in situ, which means they were born in the Milky Way, often in the disk, and accreted, so born in external galaxies, and then accreted onto the Milky Way in merger events. And much of this is only possible because of the Gaia Observatory, which was launched about 11 years ago now. We're really in a golden age of galactic archaeology due to this extraordinary data that we have from Gaia. So it measures a range of things, many of them dynamics related. So it measures on-sky positions with extremely good precision. It measures distances to stars using parallax, which is essentially when the Earth moves around its orbit, the stars shift slightly in position relative to a distant background. So that tells you how far away the stars are. It also measures line of sight velocities. So this is the velocity component pointing away from us or towards us. This is using Doppler shifts and on sky velocities. So these are proper motions. So it's just the angle that a star moves per year in milliarc seconds. And it also measures stellar spectra from which you can obtain various stellar parameters and chemical abundances. So there's an enormous amount of information that Gaia provides, including these six components of the position and velocity. So we're in a three-dimensional universe, of course, so we have three coordinates that tell you where a star is in space, three coordinates which tell you how it's moving, and Gaia can provide all six of these, which tells you an enormous amount about how stars' orbits evolve over time. So I've got a video here which just demonstrates um, parallax and proper motion. So this is greatly exaggerated, so you wouldn't see this um, in reality, of course. So it's first showing parallax. So we're just looking at a section of sky, and this is over, and you see the stars trace out little ellipses over time. So this is due to the Earth's motion around the sun. So the stars which move the most have the greatest parallax, and they're of course much closer. So very distant stars will hardly move at all. And you can see the constellations will be slightly distorted throughout the year as the Earth moves around its orbit. This is many, many times exaggerated. I think it's 100,000. So obviously you would not notice this with your eyes. But this is how Gaia determines distances to nearby stars at least, and distant ones as well. It's now showing proper motion. So as time passes, these stars will move on. As the stars move on their orbits, they'll of course move across the sky, and their positions will change. And Gaia can measure these. They're extremely slow, of course, in nearly all cases. So it's remarkable how precise Gaia can measure these. But this gives you the orbits of the stars. So this is the classic view of the Milky Way provided by Gaia. This is not actually an image. So this is not taken with it's not stitched together from many photos or anything. This is just Gaia data. So each point on this image is a measurement from Gaia of a star and its color and its magnitude, all plotted on the sky. And you can see this beautiful image of the Milky Way, including the various satellite galaxies, which I'll come on to in a minute. So I'll quickly give a brief overview of our position in the Milky Way and its different components that Gaia can help unravel. So this is a typical view you'd have of the Milky Way. On the left, you're looking down onto the plane of the Milky Way. You can see the nice spiral arms in the disk. The sun's located about halfway from the center to the outskirts. In the center of the Milky Way, we have this bar structure which rotates. This is something I've studied a lot. It's very interesting for dynamics of stars. The right-hand panel shows the view edge onto the disk. So again, it shows the sun. The disk is where most of the stars are located in the Milky Way. These are stars born in the Milky Way itself. This is where all the young stars are. And this is above and below this disk, you have the stellar halo, which is from a galactic archaeology point of view, it's actually much more interesting than the disk. There are far fewer stars. If you look at the night sky, you'll see barely any stars in the stellar halo. But that's where all the material accreted from external galaxies will end up. And that's where we can unravel the merger history of the Milky Way. That's also where the globular clusters mostly orbit in the stellar halo, although some can be associated with the disk as well. Right, this plot here now shows, this is now looking top down onto the disk again. The sun's located at the middle, and this shows many of the open clusters and nebulae that you'll be familiar with. So you can see the Orion Nebula near the sun here. Various other things like the Lagoon Nebula over here, the Eagle Nebula, various open clusters, M37, 36, 38. And just to give you a sense of how far away these are compared to the size of the Milky Way, I'm going to shrink this image and overplot it on top of the other one. So all of those open clusters, all of those nebulae that you're very familiar sights in the night sky occupy this quite small portion of the Milky Way's disk, and there aren't many objects other than globular clusters that are much further away, certainly not in the disk of the Milky Way. So you won't see many clusters or nebulae that are on the opposite side because they're hidden behind the central regions and behind the bulge. Looking a bit further out, the Milky Way is surrounded by a halo in which orbit many satellites. So I've already mentioned the globular clusters. These are generally further in, so many of them are within the sun's orbit. They're shown in blue here. And there are also many dwarf galaxies. So the most famous, of course, are the Large Magellanic and Small Magellanic Clouds here. There's also the Sagittarius dwarf galaxy here. Various others like Fornax, Leo 1, which are faint, but still, you can still see them with a reasonably small telescope if you've got good skies. But there are also many what are called ultra faint dwarf galaxies, like Bootes 1, for example. And these can't be seen in images at all. You can only see them by counting stars in a particular area and identifying them as belonging to the same object. Because the universe is dominated by very low mass galaxies, there are actually many of these in the halo in the Milky Way. Many that we won't have even discovered yet. Zooming out even further, this is the Milky Way's position in the local group. So Milky Way, Andromeda Galaxy, Triangulum, and again, many much less massive dwarf galaxies surrounding that are in some sort of orbit around the local group. So for the rest of the talk, I'm going to give a story of the Milky Way as it came to be today, from its origins 14 billion years ago to today and into the future. So the first few billion years are what I'm classing in my very simplified narrative as the formation years of the Milky Way. So this is when the Milky Way formed from the large-scale structure of dark matter and gas into something you can call a galaxy that might be recognizable as a disk galaxy, as we see today. So this is a nice recipe for how to make a Milky Way-like galaxy. The ingredients are very simple. All you need is dark matter, quite a lot of dark matter, and hydrogen. So dark matter is, as I mentioned, the dominant form of matter in the universe. It's nearly all the matter essentially is in dark matter, sort of 80% roughly. I can't remember the exact number, but it's essential for forming galaxies. If you just had gas in a universe, you could not form gravitationally bound structures because the gas would have, because it has pressure, it has temperature, the repulsive forces would overcome the gravitational attraction because gravity is extremely weak. So you need something like dark matter, which only interacts gravitationally. So the first step so you have, about 1 trillion solar masses worth of dark matter, which is an awful lot, and about 10% of that of hydrogen gas, which you need to make stars. So the first step is to make a gravitational well from dark matter. So I'll show a simulation in a minute that might illustrate this better. But you need to make some sort of gravitational potential for stuff to fall in, for gas to fall in and then form stars. Once you've done that, you can get hydrogen to fall into this gravitational well. So we call it dark matter. We call it a dark matter halo, the bound structure. So once you've got hydrogen in there, you need to cool it in order to form stars. Specifically, you need to form hydrogen molecules. Hydrogen atoms are not enough. So once you've formed hydrogen molecules, these make up giant molecular clouds, which can then collapse to form stars. Alongside all of this star formation, you also have accumulation of smaller galaxies merging from outside. So these will accumulate in the halo of this galaxy and produce lots of what we call substructure, which you can look at and uncover the history of these mergers. Now, this is enough to form a galaxy, but to form a disk galaxy, you need to let the gas settle in some sort of plane. So the gas will somehow radiate energy and then settle into a disk formation. So where it's rotating, flattened rotating situation. And then to form a disk of stars, this gas needs to repeat step 3, form giant molecular clouds, and collapse to form stars. So another invaluable tool alongside observational data is cosmological simulations. So we can look at all our observations of objects, substructure in the halo of the Milky Way, and compare this with models from cosmological simulations. So these are extremely sophisticated simulations of galaxy formation. So they include many different types of particles. So they have dark matter particles, they've got stars, gas, and sometimes black holes. They take into account the expansion of the universe. So you started off with cosmological parameters like the fraction of matter, that's like the dark matter fraction and so on. And the universe would expand. It takes into account both gravitational forces and hydrodynamic forces, so pressure, in other words, of gas. It has star formation, so you just start off with a sea of gas. Then this can, once the gas particles in the simulation reach certain conditions, they will form stars. They also have feedback, which is a very important effect. I'm not going to talk about much in this talk, but once you form stars, the radiation from these newly born stars will expel the gas from a galaxy, which makes it harder to form more stars. And active galactic nuclei can do the same thing, so they can expel the gas. Then you end up with less star formation than you would otherwise. So that's a very important effect to include. And these are extremely can produce very realistic analogs of the Milky Way. So I've put several examples here in this figure. There are various types of cosmological simulation. So the top left corner is dark matter only. The reason why you'd run this is it's just much quicker to run. If you don't have to worry about pressure forces of gas particles and so on, you can just form these dark matter halos with no galaxies in, which is not particularly useful for galactic archaeology, but it may be interesting if you're interested in cosmology. If you want to form a galaxy, you have to put in gas particles and these effects such as star formation and feedback. And once you've done that, you can form analogs of the Milky Way. These are shown in the top right. So these are all simulated galaxies, many of which are chosen by their mass to be similar to the Milky Way. So we can look at these, compare these with our observations, and make inferences about the past merger history of the Milky Way. So I'm now going to show an example of a cosmological simulation. I'm going to show it several times in this talk through various stages to illustrate these various stages of galaxy formation. So I'm going to start off at the Big Bang, essentially, or soon after the Big Bang. There are various panels in this figure, so we'll go through them one at a time. The bottom left shows the dark matter. It doesn't show it yet, but it will when I've started running it. So this is just the large-scale structure of dark matter. It forms filaments, that these collapse to form dark matter halos. The big plot in the middle shows the gas. On the lower right, the left-hand one is stars. And then this is zoomed in gas on the bottom right, the right-hand panel. So we start off by all this gas collapsing to form, collapsing into this dark matter halo that's formed. Bottom left, you can see this halo of dark matter connected by lots of filaments to different halos. And along these filaments, other galaxies come and merge. So you can see a few different galaxies on the right here coming and merging. But something to notice here is that the stars in the Milky Way do not form a disk. They just form a big sort of amorphous blob. So there's a merger going on there with a smaller galaxy. Until we reach this point here. And at this point, you can see that there is if you look at the stars in this panel here, this is looking edge on to a newly formed disk. So about 3 billion years after the Big Bang, the all that amorphous gas that we saw earlier, here for example, has flattened and produced a disk of stars. So the formation of the Milky Way's disk is one of the first interesting things that we can look at in the Milky Way's history. But before the disk, we have this sort of amorphous mass of stars and this sort of turbulent gas that's being funneled in. And this is something that's been observed in the Milky Way. So this has been named the poor old heart. So it's poor because it's low in metals. So the reason why it's low in metals is because the gas in the universe starts off as dominated by hydrogen with very small amounts of helium and like nothing, no iron, because to form iron you need to produce stars. So the very first stars will have very little iron or zero iron. The next stars after that will have a bit more iron, but will still be much lower in iron abundance than stars formed recently. So to look at the oldest stars, we want to look at the stars with lowest iron abundances. And by the way, if you're thinking, why don't we just look at the ages of stars? Ages are very hard to calculate. So metal abundances, metallicities, tend to be much more useful. So there's this population that we see in the Milky Way, shown on the right here. So the white dots show where it's observed, the density of this on the sky. So this is looking towards the center of the galaxy again. And you can see it's quite centrally concentrated. Whereas in the Milky Way plots I showed before, the disk was visible across all longitudes. This is only visible in a very centrally concentrated region. The other thing to notice is that it's not in a disk formation at all. So it's very sort of spheroidal. It extends far above and below the plane. So represents a very ancient core of the Milky Way that was formed before the disk grew. And it's been variously called the poor old heart or aurora, essentially because it was discovered by different people around the same time. And this is something that happens quite a lot in galactic archaeology. There's no standardization of names, which means that we have a bit of a mess of people coming up with names for different things that often end up being the same things. Someone needs to sort it out at some point, maybe after Gaia has finished producing data. So that's before the disk. Now, the disk formation happened a few billion years later, maybe 2 or 3 billion years after the Big Bang. We still can't be completely sure. As I said, metal abundance can be used as a proxy for age in a given galaxy. So as time goes on, stars produce more iron that enriches the interstellar medium. So therefore, subsequent generations of stars will have higher abundances of iron. So if you look at very low metal abundances, you're looking at very old stars. Now this figure here shows this metal abundance on the x-axis plotted with the circular velocity of stars, or the azimuthal velocity. Now that's the component of the velocity that points around the galaxy. So you can decompose the velocity of stars into radial motion, circular motion, and vertical motion. So the vertical motion would be up and down, above and below the plane. This shows circular motion versus metal abundance. So if stars are in a disk, you'd expect them to be at around 200 kilometers per second in circular motion. So at higher metal abundances, so these are stars that would be formed recently up here on the right, they have circular velocities of around 200 kilometers per second. As you go back in time, this is no longer true. So if you go below -1, the average circular velocity almost vanishes. It goes to around 0 or certainly less than 100. So there's no disk at this metallicity, this metal abundance. And as you increase the metal abundance from this point, you can see there's a transition. The average circular velocity increases from around 0 up to 200. So this transition represents what we call the spin up of the disk, where the point at which the gas settled from this sort of turbulent amorphous mass that we saw in the simulation into a flattened rotating configuration, which then formed these stars. So that's the spin up. The splash is something else which I may mention later if I have time. But what we're saying here is the formation of the Milky Way's disk. So that concludes the first chapter, we've got to the point where we have a Milky Way that's in a disk-like configuration. We've got some form of disk. It's not a particularly thin disk, so it's still quite puffy in the vertical direction, so above and below the plane, but there is a disk there. So the next chapter in this story is the next 3 billion years. It takes us up to about 8 billion years before the present. And this uh, era in the Milky Way's history is dominated by one big merger event. So let's return to the simulation. Let's start off at 3 billion years after the Big Bang again. So we've got this nicely rotating disk galaxy. And now you'll see in the top up here that there is a new galaxy that's just arrived in the halo of this Milky Way analog. Now, in the next couple of billion years, this is going to come and merge with the central galaxy. And if you just watch what happens when it comes and merges, it has a quite dramatic effect on the disk. So the disk, it changes orientation for a start. It gets, let's go back in time a bit to the point at which it collides. So this is the merger event here. So the disk gets what we call splashed. So this is what I actually showed on the slide before. If I go back in time a bit. So this splash thing here is where a merger event has caused stars to come out of the disk and go into their halo. So they've lost a lot of their circular motion. So that's what the splash is. But moving on. So this is obviously a simulation, but there is a similar event that occurred in the Milky Way's history as well. So this can be seen if you look in this is velocity space. So again, we're looking at the circular motion on the y-axis. So this is circular motion kilometers per second, the velocity around the galaxy. So again, in the disk, you see the disk is at about 200 kilometers per second. On the x-axis is showing radial motion. This is the component pointing away from the center of the galaxy. Now the disk is at about 0 because stars in the disk are on roughly circular orbits, so they just move with no radial motion at all. But what Gaia revealed in 2018 was that when you look at lower circular velocities, you can see there's this structure which extends to very large and very small radial velocities, so above 300 kilometers per second radially. But it's moving as fast as the disk is, but in a radial direction. So this is called, again, this is discovered by two different groups at around the same time. One of them named it the Gaia sausage, as you may be able to see why, because it roughly corresponds to the shape of a sausage. The other group, being a bit more pretentious, called it Gaia Enceladus, named after Greek mythology. But the origin of this, as I've already mentioned, is that this was formed in a merger event with a large satellite galaxy. So this is another simulation. This is not a cosmological simulation. This is much more idealized. It's just manually set up with a central galaxy and a satellite galaxy, and then they come and merge. So the Gaia Enceladus, we tend to call it the GSE. It was formed by a merger about 8 to 11 gigayears ago, as we saw in that simulation, with a dwarf galaxy that was roughly 10% of the mass of the Milky Way. That number is still quite uncertain. But the reason why those stars are on such highly radial orbits, so very little circular motion, is because the orbit of this satellite became highly radialized before it merged with the Milky Way. So I'll replay this video. The mechanism for this radialization is a process called dynamical friction. So unlike actual normal friction, this is due to gravity. And it's what happens when you let a large mass, such as a dwarf galaxy, pass through a sea of lighter particles. And because as it moves through, these lighter particles get deflected around it, and this transfers momentum from the dwarf galaxy to this sea of particles. In this case, the sea of particles is the dark matter of the Milky Way. So as the satellite galaxy comes in, you can see it slows down, loses energy as a result of dynamical friction. And of course, this isn't what you'd have if you didn't have dynamical friction. You don't have this with planets; they don't come spiraling in, losing angular momentum. But because of dynamical friction, you can lose angular momentum and produce these highly radial structures. So this is roughly what the gas sausage Enceladus debris looks like in the Milky Way, and it comprises quite a large proportion of the halo of the Milky Way near the Sun. Now, if you want to go and observe the Gaia Sausage Enceladus, you may not be able to see many of its stars, but you can see several of its globular clusters because all galaxies above a certain mass will come with their own population of globular clusters. And the Gaia Sausage Enceladus is no exception. So it brought about 20, roughly, globular clusters to the Milky Way. And this includes some quite bright ones that you'll be familiar with, such as M2, M56, M75, and M79. So these are shown, some of these are shown on this. This is the same spaces I was showing before, circular motion versus radial motion. The Gaia sausage is kind of shown by this ellipse here. And the circles outlined in black are these Gaia sausage Enceladus globular clusters. And you can see they're on highly radial orbits. So they're moving with very little angular momentum. There are various other ways that you can determine that they're from the GSE, not just this motion, such as their chemistry and their ages. So yeah, if you want to go and see the Gaia Sausage Enceladus, look at one of these globular clusters. And it led to this exceptionally good paper title, The Sausage Globular Clusters. I happen to know all these people. That was a good paper. Another event that occurred during this period of the Milky Way's history is the formation of the galactic bar. So I showed the bar before. It's this long extended structure in the inner five kiloparsecs, so about 15,000 light years roughly, which formed again. This is something that's reasonably uncertain, but we think it formed around 8 billion years ago. We don't really know why, but there are two main reasons why bars form. One is that the disk becomes unstable, so it's actually quite easy to form a bar because a disk configuration of stars with stars on circular orbits or near circular orbits is not very stable. But you can also form a bar with tidal effects from a passing mass. So the Gaia Sausage Enceladus satellite, as it comes in, will cause tidal effects on the disk. Tidal forces could form the bar as well. So it could be some combination of these, or it could be one or the other. There is evidence to suggest that you can form a Milky Way-like bar with the Gaia Sausage Enceladus-like merger. Okay, moving on to the most recent 8 billion years. And most of the interesting phase of the Milky Way is actually behind us at this point. The Milky Way is actually unusual in that it doesn't have a particularly exciting history in the last 8 billion years. But there are a few exceptions. So with restarting where we left off before, we've got this disk rotating. The disk obviously continues to grow as time passes. So the disk is where the stars are forming in giant molecular clouds. This will continue to grow and form stars. But there's very little else that's happening. There aren't any big merger events disrupting the disk like we saw with the GSE. And there are just a few satellite galaxies you may be able to see floating around in the halo. And then there's this big one that comes in right at the end. So this is again similar to the Milky Way. We do have a large satellite galaxy, the Large Magellanic Cloud, which is in a similar situation. But before I come on to that, there is one event which happened before the Large Magellanic Cloud came in. So this is the Sagittarius Dwarf Galaxy. So the Sagittarius Dwarf Galaxy, or SAG as it's usually called, is located obviously in the constellation of Sagittarius. It's shown on this Gaia sky map with this red ellipse. So you can just about make it out in this. You may be able to see a slightly brighter patch here. It's this elongated structure sort of runs perpendicular to the plane of the galaxy behind the galactic center. So it's on the far side of the galaxy from us. So this is the third most massive satellite galaxy of the Milky Way after the Large and Small Magellanic Clouds. As I said, it lies on the opposite side of the center of the galaxy. But it's not just a nice bound galaxy anymore. It's undergoing ongoing disruption. So the stars have been stripped by tidal forces um, from the cluster, sorry, from the galaxy, and they extend around these multiple wraps around the galaxy in what's called the Sagittarius stream. So this is one of many examples of streams, stellar streams in the Milky Way. This is what happens when tidal effects pull the stars out of a bound object, and then they get spread along the orbit. So this is a simulation of the Sagittarius stream. So the sun's shown with the yellow star. So the Sagittarius dwarf galaxy comes in, then as it passes close to the lowest point of its orbit, stars get stripped from it. They extend out and form these coils around the galaxy. And there are multiple wraps of this. And like the Gaius Sausage Enceladus, Sag also brought its own globular clusters. So probably the most famous example is M54, which lies right at the center of the remnant of Sagittarius. So although Sagittarius itself wasn't discovered until 1994, but of course M54 is much brighter, so it's been known about for many, I don't know when it was discovered, probably a few centuries now. So it lies right at the heart of the Sagittarius core, and it may be the nuclear star cluster of Sagittarius. So the nuclear star cluster is like a globular cluster, but it has a slightly more complicated history of star formation. So it's not quite the same, it doesn't have quite the same history. And this may represent the nuclear star cluster of Sagittarius, which is quite exciting. Another one which is notable is NGC 2419, which is I think it used to be thought to be unbound to the Milky Way on an intergalactic orbit, which is why it's called the Intergalactic Wanderer. But this also lies in the Sagittarius stream, and I think it's been confirmed that it is associated with Sagittarius as well. So this figure here shows on the x-axis is sort of angle along the stream. So it's like a longitude coordinates along the stream. So the yellow points show stars from Sagittarius that have been stripped to form the Sagittarius stream. The y-axis shows distance from the sun. And there are all these globular clusters, all of which can be associated with the Sagittarius stream. And then there are these few up here, these stars up here, which overlap with NGC 2419. So I think it's thought very likely now that it's associated with Sagittarius and was originally part of Sagittarius before it was stripped to form part of this stream. So I mentioned that there are other streams in the Milky Way other than Sagittarius. This is an iconic image of the northern sky, I think, from the Sloan Digital Sky Survey, and it's coloured by distance here. And you can see the Sagittarius stream here is dominant, so it covers a vast area of the sky. It wraps around the whole galaxy, so it will actually go around the whole sky. And it's quite interesting in itself. You can see there's a bifurcation here, so there are two different arms of the stream. But there are other streams here. So there's one called the Orphan stream here. It's called the Orphan stream because we don't know where it came from. So streams can be produced by either dwarf galaxies or globular clusters. There's no globular cluster that corresponds to this stream. So it could be a globular cluster that's been completely dissolved. Another one, which is probably the archetypal stellar stream, is Palomar 5. So this is a globular cluster that's still in existence. You can see the bright dot here, and then it's got these two tidal tails which extend either side of it. So this is a classic image showing all the sort of the debris that you can see in the stellar halo of the Milky Way. By the way, the Hercules Aquila cloud and the Virgo overdensity are associated with the Gaius Sausage Enceladus. These are the two. If you remember that that simulation with the red dwarf galaxy, that sort of extended structure. These are the two ends of that extended structure, we think. So I've got another nice simulation here showing how you form a stream from a globular cluster. So a globular cluster, like Sagittarius, can also lose stars by tidal forces. So stars get stripped by tidal forces, just like tides on Earth. But if you imagine there are super tides where the water, instead of just rising a few meters, got pulled all the way out of the Earth's gravitational field. Globular clusters form cold stellar streams. So this is in contrast to Sagittarius, where we had this sort of broad structure. Cold globular cluster streams tend to be much narrower, which makes them useful in themselves. They roughly trace out the orbit of the cluster, which can be useful for determining the shape of the Milky Way's gravitational potential, which is one reason why they're so useful. Like the orphan stream, globular clusters can be completely destroyed by this process. Gaia has helped to discover, I think, well over 100 of these now in the Milky Way. So sadly, you can't go and observe them because they're extremely diffuse. I think these points correspond to stars, so you can see how few stars there actually are. There's such a low density. But they do cover an enormous span of the sky, so many tens of degrees in some cases. And this plot just represents a handful of the stellar streams that have been discovered in the Milky Way by Gaia. So it shows Power 5, for example. That was discovered before Gaia, but most of these were discovered using Gaia data. Right, so the final event that's happened in the Milky Way's history to date is the arrival of the Magellanic Clouds. So these have only come onto the scene very recently, in the last billion years or so, 1 or 2 billion years. So they're the most massive satellites of the Milky Way. They're probably only on their first orbit around the galaxy. But they're having a profound effect on the Milky Way. So because they're so massive, they're pulling the center of the Milky Way towards them, which means that the Milky Way is pulled out of equilibrium, which can have quite weird effects. So, for example, stellar streams can be distorted and sort of twisted. This is quite useful because it means we can measure the mass of the Large Magellanic Cloud. But yeah, there are all sorts of interesting effects that the Large Magellanic Cloud is having on the Milky Way, and it means we can't just assume the Milky Way is a nice equilibrium configuration. It's being constantly sort of pulled and twisted out of its current configuration. So that's the last event that's happened so far in the Milky Way's history. There's, of course, one more big one to happen in the future, which I'm calling the final chapter, and it's often called Milkomeda, i.e. the merger of the Milky Way and the Andromeda Galaxy, which is likely to happen in about 4 billion years. So I often think it's quite ironic that the most famous merger of the Milky Way, the only one that someone on the streets is likely to know about, is one that hasn't even happened yet. No one knows anything about Gaia Sausage Enceladus. But this would be the biggest event in the Milky Way's history if it does happen. So in about 4 billion years, the trajectories of the Milky Way and M31 will bring them together to collide in a major merger. So most of the mergers that the Milky Way has undergone are called what you call minor mergers. So in other words, the mass ratio is quite large, whereas the Milky Way and Andromeda have quite similar masses. So they would both be likely destroyed in the process and to form a giant elliptical galaxy, as shown in this very nice visualization of Andromeda approaching and then causing a starburst, so lots of star formation before star formation is completely stopped by this elliptical galaxy forming. And I imagine much of the gas would be driven out of the galaxy, so you wouldn't be able to form stars anymore. So this would be kind of the end of the life of the Milky Way. So I will stop there. Thank you very much for your attention. I'll leave you with a simulation of the Milky Way undergoing its final merger to form Milkomeda.
Well, that was great. Thanks very much, Adam. I should have mentioned before, if anyone's got any questions, if you could put them on the Q&A. So just click on the Q&A icon and ask away. And anyone that's on YouTube, if you'd like to post any questions on the chat, I shall try and read those out as well. Just a quick question from me, Adam. You talked about the globular clusters that arrive from mergers, but there must be a lot of the globular clusters that formed in the early stages of the galaxy as well.
Yeah, most of them, I think most of them are in situ. So they formed from the gas in the Milky Way. Yeah.
But the process for that's presumably not very well understood.
No, we don't know very much about how globular clusters form. I mean, the James Webb Space Telescope is providing very interesting images of early galaxy formation, and it looks like most of the star formation in these early galaxies, or much of the star formation, is in giant globular clusters, which then dissolve. So maybe, yeah, maybe JWST will help unravel the formation of globular clusters a bit more. But yes, it's not something that's fully understood.
So, and on the formation of the disk, is that aligning with the threads of the cold dark matter of the early universe, or is it just
Well, so
on,
you're asking if there's any correlation between the disk alignment and the
yeah.
scale structure. Yeah, that's very interesting. Um, because I mean the orientation of the disk is the kind of the sum of all the angular momentum that's been accreted from the large scale structure. So I think yes, there'll be some correlation. This is something I did on my master's project actually several years ago, looking at how mergers like the Gauss Enceladus can realign disks. So they tend to realign disks towards the plane of the merger event, as you'd expect. If you've got a merger event coming in a particular plane, the angular momentum in that direction will get transferred to the host galaxy. Yes, it's an interesting question. I'm not sure how it correlates with large scale structure. Um, that is something that's, yeah, quite interesting to think
Hmm.
about. I'm sure someone has done work on this, but I'm not sure.
There's a few questions on the Q&A. So Alan's asked, there was a S&T article, Sky Telescope, about 5 years ago suggesting we had slightly underestimated the mass of the Milky Way, and in fact it's a bit larger than Andromeda. Is that accurate?
Um, I think from what I thought, it was thought to be less massive than Andromeda by, I don't know, is it a factor of, I can't remember, maybe a factor of two-ish less massive than Andromeda. I mean, ultimately, we don't actually know the mass of the Milky Way's dark matter halo because you can't see it, obviously. And to measure the mass of the dark matter halo, you need some sort of tracer particle, like stars or satellite galaxies that are far out. And we do have some of those, but there's a lot of uncertainty because they're so far away. So yeah, we can't say for sure whether the dark matter. Obviously the dark matter dominates the mass because it's about 90% of the total mass or more, probably more. So yeah, we can't say with confidence that whether the total mass is larger or smaller than Andromeda, but I think I think we can probably be pretty sure that the stellar mass is smaller than Andromeda.
I presume it's the same for Andromeda. You can't know how much dark matter it has either.
Yeah, exactly.
Yeah. Rob asks, at what point did the central black hole in the Milky Way form?
Reasonably early. So it would have been, again, this is something that's not fully understood because it's a bit of a problem how you can make black holes so massive so early, but it would have been in the first, I don't know how many tens of millions of years, but it would have been in the first billion years, I believe.
And Paul has asked, can we actually see the star trails as globular clusters orbit the Milky Way?
Well, you can't. You certainly wouldn't be able to.
or image them from an amateur viewpoint with a largish telescope, I suppose.
Pretty much impossible, sadly. So
Hmm.
the only one, I mean, the Sagittarius stream was only discovered in like 2006 by the Sloan Digital Sky Survey, and that was taking multiple measurements across the whole sky. Palomar 5 is probably the earliest globular cluster stream to be discovered, I think. But that was again only 20 years ago with very large telescopes and with a lot of um, data processing afterwards. So really,
I had a look at one of the papers about the Palomar 5 stream and wondered if that might in any way be doable by an amateur. It's probably a bit at the limit, maybe.
I think it would probably be a bit difficult, yeah. I think you need to, I mean, to really see a stellar stream, you need to use some other information about stars, such as,
So the color, basically, I suppose, really.
yeah, or now we've got Gaia, you've got proper motions, so you can
Mhm.
isolate stars moving in the same direction. Obviously, that's not going to help with imaging, but
Yeah, yeah, yeah.
yeah, it's very hard. I'd be very impressed if someone did.
The challenge for you, Paul.
I ask a question if there's
Yes.
a slot. um, I was intrigued by the association of the globular clusters with the streams. Do you know they're part of the stream simply because they're spatially associated with them, or is there some characteristic of the stars within the globular that matches the streams, if you see what I mean?
Do you mean Sagittarius in particular?
Yes, yes, Sagittarius stream, and the others indeed you were showing.
I think it was velocities as well. So
Okay, yes.
we can measure proper motions of globular clusters. Gaia can do that as well as stars, individual stars. And I don't know, there may be some line of sight velocity measurements as well. But yeah, it's velocities as well. You can show that if they're co-moving in the same direction, there's a high confidence they're part of the stream. Yeah, there may also be some use of ages or chemistry as well,
Mm.
if they match.
Mm.
Certainly that's true with the
Question
Gaia sausage Enceladus clusters.
question on YouTube. Is most of the visible mass contained in galaxies or the numerous globular clusters and satellite galaxies?
Um, most of it is unbound. I mean, most of the mass, of course, is in dark matter. But if you're
Yeah,
talking about stars, then
invisible mass. Yeah,
yeah, most of the stars are in the disk, so unbound.
yeah.
Obviously, they're born in open clusters, but open clusters dissolve very quickly. So most of the stars are just field stars in the disk, or in the bar.
And there was just a comment saying thanks for the fascinating presentation. And sorry, they came in a bit late, so I'm going to rewatch it afterwards. Well, if there are no more questions, I'll just thank Adam very much for his presentation tonight. That was really interesting. It's I think fills in a lot of gaps in people's knowledge about what's been happening with the evolution of the Milky Way, and certainly it's been things I've been learning since recently, and my astronomy knowledge is all all very dated now. And it's great to get an update today from you, Adam. So thanks very much, and I really appreciate you speaking to the members of the association tonight.
Thank you.
And if you want to hang out, maybe there's the last question here. Oh, Steve says, thank you. Excellent. Oh, yeah, I quite agree. Great, thanks very much. If you want to hang around, Adam, to hear about galaxy observing with the the naked eye, you're more than welcome. And we'll move on to Jim's talk. I think you're still sharing your screen, Adam. There we go. So our next speaker is Jim Latham from North Wales. It's not Mrs. Trellis. Sorry, I haven't a clue joke if you're unaware of Mrs. Trellis from North Wales.
I've started to share if that's working.
Yeah, that's coming through great now, Jim. Thanks. So Jim actually gives this or versions of this talk to the Web Society. I wasn't able to go to the Web Society meeting in the summer, so yeah, I suggested you might want to have a rerun of it and talk about the limits of visual galaxy observation, which is something I'm really interested in, and I expect any folk who didn't manage to get to the Web Society meeting will be interested to see it, or even to see a rerun of it, even if they hadn't seen it the first time round. So I'll just quickly pass on to Jim to talk about exploring the limits of visual galaxy observation.
Thank you, Callum. Yes, it's going to be quite a stark contrast to Adam's talk, which was true high science, and really going to hear about things I can see from the shed at the end of my garden. So it's a really very different scale. And apologies to those of you who've heard it before. By way of an overview, then, I'm going to give a bit of an introduction, a little bit about myself, actually, because I've recently had a lot more to do with the dark sky section and the BAA generally. A lot of you don't know me, so I'll say a little bit about my observing past. Then I'll go on to talk about my little galaxy project, basically trying to work out how faint a galaxy it's possible to see with my current setup. And I'll give you some results, and then a little bit about what happens next. As a kind of caveat, I should say that I'm not an astrophotographer. So all the images of galaxies in this presentation are from the digitized sky survey delivered through various means. So I've no credit myself for the photos. I've been observing for a long time. This is me going back a very long time indeed, back to the 1970s, when I was quite obsessed with observing with a 4.5-inch reflector at the time. This is my original Northern Star Atlas, bought as new and now well worn, as you can see, over the years. So it's a long history of observing. Going forward into some teenage years, I upgraded to a Celestron 8, which is still going strong, and the central image there was taken just this summer, so the telescope itself is going strong. Use that for an awful lot of deep sky observing and planetary observation. Then following that, life intervened, as it does with all the progress of university and families and jobs. I did less and less observing through an observatory, my own observatory, more reliance on things like meter observation that didn't take a lot of equipment. So there was a rather hiatus, if you like, in observing, until relatively recently, when I've found myself equipped with this current setup, which is a 14-inch Newtonian telescope from Orion Optics, which I have mounted on a sort of almost home-designed yoke mount made by Beacon Hill Telescopes, which is a wonderfully stable mount, actually. Really lovely design for visual observing. It's driven and works very, very nicely. The eyepiece tends to be at a very convenient position as well. So it's a really good, solid observing setup. And I have this in a runoff roof observatory, illustrated here, which also works very smoothly and very pleasantly indeed. When I established all this and got this kit in, my interests were quite diverse. I was thinking I was going to be doing a lot of planetary observation. I was hoping to get into astrophotography in quite a way too. But things didn't really work out quite like that. I found that once I started looking at the sky through it, visually at deep sky objects, I was really quite hooked again by just simply what I could see. And the real revelation, I think, came from looking at this object, NGC 7331 in Pegasus. which in itself is a fine galaxy to observe. But what really struck me were these background galaxies, the so-called fleas, which are listed in most accounts as between the 14th and 15th magnitude. And I was quite astonished at the time that it was actually quite easy to see these galaxies from a telescope. And really, that was the start of a bit of an obsession, if you like, of seeing just how faint a galaxies I could really pick up based on the star charts and information I had available. So moving on then, over the last few years, I've seen several hundred galaxies and recorded them, and sort of noted the reported magnitudes, etc. Reported magnitudes often seem to be a bit suspicious, and I was picking up galaxies that by the reported magnitude just seemed too faint, or the magnitudes, the way they were reported themselves, and things like stellarium seemed surprisingly consistent or clustered. It seemed to be a bit odd. And the reported magnitudes themselves tail off at about the 15th to the 16th magnitude, which is coincidentally about probably the limit of my observing setup. So there were sort of inconsistencies as to what I could see, and I was just intrigued as to really what was going on. So I started to form various questions in my mind, really, simply how faint a galaxy can I visually observe with this setup? And really, what factors determine this? Is magnitude the most important thing, or is something else like surface brightness actually more a factor involved in this? So to answer these questions, I began some more systematic sampling just over a year ago. In fact, it's not a great time base there, but really to look into this in more detail. And I should say at this point, my background, my doctorate was in ecology, looking at deer populations throughout Scotland and relating that to a whole host of environmental variables. And this involved a big sort of data crunching exercise using multivariate statistics. So I tend to think through big data sets and how you might analyze them to look for patterns. And one thing that immediately struck me really is the sample is biased, because essentially I've just got galaxies I can see. If I really want to see what the difference is between the cutoff from what I can see, I also need a sample of galaxies that I can't see, which can seem a little perverse, but it's that was the question in my mind. So I set about this little project, the Galaxies Not Seen project, which is basically a systematic recording of galaxies across an area of sky, and based on star catalogues, just to see what could be seen and what couldn't. So I predetermined selected areas of sky using stellarium base mapping, just basically worked through that to identify which galaxies I could see and which I couldn't. This was generally working at pretty high magnification, usually sort of 300 to 500 magnification, so very sort of intense, detailed work. And I tried to reduce the variation in the sky conditions by having certain parameters here. So I'd only look for the galaxies when the moon was out of the sky, it was beyond the astronomical twilight, looking at areas of the sky above 50 degrees altitude to reduce the atmospheric dispersion there as much as I could. Only with transparent skies, by the skies here when the Milky Way was visible, in fact, and allowing at least 45 minutes of dark adaptation, just to try and take as much of that kind of variation out of it as I could. So this is just an illustration of the sort of thing I would do. I would take a screenshot in advance of the areas I was going to look at on the smartphone. So that's a typical example there. And you can see the string of pretty faint galaxies, a brighter NGC one there and throughout. So I would simply star hop through that section of sky, just recording whether I could see the galaxies or not. And then once I completed that slide, I'd move on to the next area and the next area, which are slightly overlapping. I have to say, it's quite grueling work doing this. It's star hopping using stars at the absolute limit of vision. And whilst it can be quite easy to know if you've seen a galaxy, to convince yourself that you haven't seen a galaxy is something quite different again. So they're often, maybe half an hour staring at a hot patch of sky, just trying to see whether there was any glimmer of detection there. And your brain starts to do funny things on you. You start to see little flashes of light, and you're not sure whether you did see something or not. So there's almost like a psychological aspect to this, as to what you could see and what you couldn't. So really, it's my best judgment of what I could see in this process. So as of April this year, I had what I thought was a fairly reasonable sample size of over 800 galaxies seen and 149 galaxies not seen, though I had looked for them. And I wanted to analyze these against, well, some consistent data to try and tease apart what was causing the difference. And I came across the Hyperlader website and database, which is administered by the University of Lyon in France, and that collates big catalogs of data around galaxies, all automatically generated from imagery. So it seemed like a good, consistent database to start to look at. And from the information available, I selected out these selection of parameters. So there's some basic stuff around what type of galaxy it was. There's a couple of things about its physical size or the apparent diameter, its axis ratio, what sort of angle it is onto us. There are a couple of measures of surface brightness here, which seem like a good thing. Surface brightness seemed to be a likely thing that would be a factor affecting visibility. And then there's a whole string here of different magnitude measurements taken in slightly different spectra, which I also picked out. And then just for fun, there's a couple of things at the bottom, like the radial cosmic velocity and an estimate of the actual total distance of the galaxy from us. So some results from all this. The first thing I did was to explore the magnitudes themselves. So this is a plot of the reported visual magnitude from Stellarium. If I could find my mouse, I could find it down there, against, in this instance, the magnitude in the U spectrum. Quite a decent relationship there. And then putting on the other ones, there's the B magnitudes, V magnitudes, I magnitudes, and K magnitudes, all of which are obviously well correlated with each other and with the reported visual magnitude, although with quite a variation around them. So there's a lot of options there for a baseline magnitude measurement, if you like. Just trying to summarize these, quite clearly the B magnitude has advantages over the others. It has the highest number of records. Over 99% of the galaxies have a B magnitude associated with them in the database. And there's a high correlation, the highest correlation of any of these magnitudes with the visual magnitude. So just looking at that in more detail, you get a plot like that. And there are outliers like this slightly odd one at the right-hand side, which is spoiling the relationship there. Just to look at that, what that is in more detail, it's a galaxy NGC 2415 in Pegasus, which I had seen, and yet Stellarium lists its magnitude as over 21, which is obviously quite ridiculous. So that's something there's obviously an error there in that database, and it's throwing things out. So removing that from it, just to clean up the data a bit, you get a slightly better relationship again. So B magnitude seemed like a good consistent basis for using for a lot of the comparisons. It tends to work that it records about a magnitude fainter than the visual magnitude. And just while I'm at it, I'm going to put some actual galaxies onto these spots so it starts to become a little bit realer. Not surprising, M31, Andromeda is down here. It's the brightest galaxy in the sky. M33 is not far behind, and M81. They all fall nicely on this central line, which was good to see, a bit of consistency there. So starting to look at what these parameters might show about what you can see and what you can't. This is just summarizing a lot of information where there's too many numbers here, really. So just looking at the last column here, this was an attempt to devise an overlap index just based on the ranges, the data there, just to see which seem to be showing the best separation. So a lower number is less overlap, and it's greater distinction between seen and not seen. So within these, some of the magnitude ones come out quite nicely, about 10 or 11%. Angular diameter, not surprisingly, the smaller it is, the fainter it is, the further away it is generally. But the surface brightness down here both came out as pretty high, a very high degree of overlap, which came as a bit of a surprise really to me. So looking at this in a little bit more detail then, this is looking at the breakdown of galaxies by their B magnitude. So in blue here, these bars, the number of galaxies seen for that magnitude, and those in orange are the ones not seen. So essentially there are two distributions. but they're overlapping. There's this broad area here where between magnitude 15.5 to 17.5 in the B magnitude scale, where there's a high degree of overlap between what could be seen and what couldn't. This is a similar plot done for angular diameter, all highly correlated again in a very similar kind of pattern. And then moving on, this is looking at one of the surface brightness measures, which is a very odd distribution, really. Bear in mind, it's based on magnitude, so surface brightness, although it looks like it's increasing, they actually become fainter along that axis. It seems that for the brighter end of it, basically, I was picking up all of them, no problem at all. When you get down to lower surface brightness, it's actually a complete mix. The distribution of ones I couldn't see is completely contained within the distribution of ones I could see, which came as a surprise. There's something slightly odd going on with surface brightness. Looking at the distinction a little bit more, this is looking at a plot of B magnitude against angular diameter, just two well correlated parameters here, but just seeing how they fall out. And just zooming in on that overlap zone to see what's going on. And you see there's a high degree of overlap there. And just to look at what's some slightly strange things, that one of the faintest galaxies of all I appear to have seen visually, which came as a surprise. So just looking at as to what that was, this is a PGC galaxy, I think in Gemini in this case. And it turns out it's not a single galaxy, it's one in a small cluster. So potentially I'm picking up the combined light of all of them, making it visible. Maybe it's an artifact, or maybe there's an error in the magnitudes here somewhere, but there's something slightly odd going on. Looking at the next one along, the next brightest one that I was, next faintest one that I was picking up. You see here it's a galaxy which has a star superimposed on it, albeit at magnitude 17. So again, there may be some superposition, some sort of combined light there, which is causing a signal that it's possible to detect visually. Looking at the other extreme, there are galaxies down at this end, which you would expect to pick up, but weren't visible. In this case, this is a UGC 800, which looks like a very low surface brightness spread out face-on spiral. So there's probably reasons why that couldn't be seen. Moving on then to another plot, this is exploring the surface brightness thing in a little bit more detail. As I explained before with the histogram thing, so down this end of the higher magnitude and higher surface brightness, basically everything is being seen, but at lower surface brightness, there's a high mix and it's very muddled scene there. Just to put on some of these galaxies for interest, these are all dwarf galaxies, very, very low surface brightness things, dwarf galaxies in our local group. Now, it's quite interesting to look at these. Leo 2 is one of these ones that has a reputation for being extremely hard to see, extremely faint, low surface brightness galaxy. I spent a lot of time looking for this, and essentially after a time you start to pick up you describe as a faint brightening of the background sky, which indicates where it is. But beyond that, with averted vision, you start to pick out just hints of like little knots of stars within it, little brighter concentrations. And I think this is part of the answer in a way to why some of these much fainter galaxies are some situations actually do become visible, because you're not detecting the entire thing, the uniform average brightness. You're picking out parts of it which happen to be that little bit brighter on average. So it's the internal structure or the variations in structure of a galaxy which may perhaps be rendering some of these visible that you wouldn't expect to be. And it's fine. The last of these plots, this is looking at, just for fun, really, it's this is an index of distance. I'm not exactly sure what these numbers relate to, but it's essentially a distance based on redshift against B magnitude. Similar kind of plot again, but there's a sort of a smear of galaxies down the bottom here, which again are all the local group galaxies, which is rather nice to see. At least they do sort of fall out together in the plot, which is not surprising, but it was quite a satisfying thing to do. So there we are. just to finish off then, I'll suggest some emerging conclusions, or at least key points from all this. Firstly, there's a high degree of intercorrelation here in these data sets between magnitude, angular diameter, and distance, as you'd expect, really. A lot of things going on. Magnitude generally being the main determinant. And the second point here, B magnitude of those available, seems to be the most consistent general indicator of detectability. But even then, it's not a clear distinction. There are other things going on. But to my mind, it's a useful parameter to have. It's possibly more useful than quoted and reported visual magnitudes for telling whether you can actually see an object or not. And they're widely available out there through the Hyperledger data set. So I feel that's a useful practical tool there. Third point is that surface brightness measures are actually very hard to interpret. I came into this thinking they were going to perhaps be the key to all this, but actually there's complex relationships going on. And I think this relates largely to the final point here, that the internal structural characteristics of galaxies are probably a very important factor in whether they can be detected or not. You get some bits of galaxies which are much brighter than the average part of it, and that is the bit you can see. So in terms of next steps, moving this work on, well, for those of you who saw this through the web presentation, I haven't really progressed this very much, but I had been thinking about it. It probably needs some more sampling at the seen not seen transition to flesh that out, to have a better data set there. There's a lot of potential for more rigorous statistical analyses. I've basically done some plots on this, but there's a lot more could be done, particularly bringing in multivariate analyses. The third point, I've got the data here, but I haven't really played with it, is the galaxy type and orientation. Are we seeing a difference between, say, spiral types and elliptical galaxies? And does the orientation they're presented to us make a difference as to how well they can be detected? Next point is, well, as I've alluded to, it's this looking at the brightness variations within individual galaxies. And there may be ways of looking at photographic catalogs online to see, how they vary in terms of brighter pixels within them, things like that. And then finally, the sky conditions themselves. So I tried to adjust for as much as I could, but there's probably potential here for looking at that in more detail to see how actual sky conditions is affecting what you can actually detect. But last of all, open question really, is all this useful? I mean, it's been an interesting exercise for myself. There's no high science in it. It's as an amateur astronomer, I find it interesting to know more about what's possible to see and what isn't, and why that is. But I'm welcome to critique of this or any comments really about the whole process. So that's it. I'd like to end some of my own pictures of galaxies, but I don't have any, so I'm going to show you some pictures of the aurora instead from May, which was a wonderful display here in North Wales. So there we go. That's the end of this. Thank you for listening.
Thanks very much, Jim. That was great. Fascinating to see how faint you can get, and that was all through a 14-inch Newtonian, of course. Yeah.
Yes.
Did you talk about sky conditions? Do you actually measure your sky brightness when you're doing your observations?
No, I haven't, and that's something that I wish I had done right at the start. Obviously, that's something you can't do retrospectively, but it would be, looking forward, if I do more of this, it perhaps would be an interesting thing to bring in. And yeah, obviously, it does vary a lot, and you can clearly by just looking, visibility varies on objects, quite a lot.
Yeah. Question online from Paul, and this is quite a long one, so sorry. Have you ever observed alongside someone using an imaging setup? One of the most fascinating experiences I've had in astronomy was when I was imaging in Texas alongside seasoned visual observers like Larry Mitchell, Barbara Wilson, and Steve O'Meara. We were able to test and prove what they were visually observing by taking a short exposure in the telescope, enhancing everyone's experience. So both techniques can contribute to our enjoyment of the hobby. So the first part of that question was, have you observed alongside anyone using an imaging setup?
Well, no, simple answer, I haven't, but it sounds like an obvious thing to do, and a very interesting thing to do. I mean, I have thought it would be useful to do some simple imaging of the extreme ones where I'm just think I've seen it. You're not absolutely sure. It'd be interesting to take an image along at the same time as well to see, what you're really looking at those occasions. But no, and it would be interesting to get different observers' perceptions as well, different ages as well. Obviously, different telescope sizes. There's a whole realm of different variables here, really.
Yeah, some younger observers maybe.
Yes.
So Alan says, my experience is that catalogue magnitudes for a particular galaxy can show variations. And as Jim noted, there are odd, plain and simple errors in the catalogues.
Mm. Yes, and
I think we've all come across catalogues which seem to have just completely wrong numbers in them for.
Indeed, Stellarium has some funny things, even for some of the Messier objects. They're not right at all. I'm taking them as face value for this analysis, but yeah, there are problems there, I think.
Paul says, great presentation, so much work and so valuable. Thank you very much. Steve asks, how many do you observe in a night? Galaxies, I guess that is.
I would treat it as a good night if I didn't see 15 to 20 galaxies. It's quite strange judging a night by how many you didn't see. But
how many would you aim to see in a night? I suppose would be the other question of the comparing the
yeah, there'd be a sample of maybe, I don't know, 20 to 30, something like that, to work through. But I found it really very tiring work because you're really working at the edge of perception for a lot of it. It's quite hard. The seen galaxies are much larger samples. I'd include all the ones I happen to have recorded previously anyway.
So you're using quite high magnification. There's this like Teleview Ethos eyepieces, or what sort of eyepiece do you use for?
I use APM eyepieces, which I think are essentially Ethos clones. It's a very similar thing, very similar specifications, but I found much more affordable. I'd be interesting to do a side-by-side comparison. I mean, I find them very good, certainly. Magnification will vary. That's another thing I would do, trying to see something. I'll try a number of different magnifications. Usually the higher magnification would bring things out with the increased sky contrast. But not always. And that's another variable indeed, actually.
So Alan's got a couple of comments. Another facet of this is the variation in quoted limiting magnitudes for given apertures by different authors.
Yes.
And as an example, Sidgwick says one of the classic books is 16.3 for a 50 centimeter, but Harting says 17th magnitude. So yeah, quite a big difference even in what you might be expected. I suspect maybe some of that's quite empirical.
Yes, I was surprised that the limiting magnitude for galaxies isn't very different to the limiting magnitude for a star, apparently. I would expect as a diffuse object for the limiting magnitude would be much lower for a galaxy, but maybe it's a factor of the way that the magnitudes are recorded or reported.
And Kevin commented, maybe you could try a machine learning approach to use galactic parameters with your observations to predict observability.
Is something that would be very interesting to do if I knew how to do it. So if anyone's interested,
maybe Kevin
collaborating
and do that.
Yeah.
quick look on YouTube and no additional questions. All right, great. Well, I think Adam has departed from the meeting. So thanks to Adam for his presentation earlier. Anyway, many thanks to Jim as well for his presentation tonight. It's a fascinating topic, and hopefully might encourage people to get out into a bit of galaxy observing, see what you can see and what you can't see as well. No, I think we might have another question on the chat here from Mike. Thanks for all the great presentations. Thanks, Mike. So yeah, thanks very much, Jim. Thanks to everyone for coming along tonight and listening live. And if you're watching this on YouTube catch up, then I hope you've enjoyed the talk. And if you've got any questions that you want to answer, or even if you've been listening tonight, any questions that you want answered, please just get in touch with me, and I'll pass them on to Adam or Jim, and hopefully they'll be able to address any questions that you might have following up. So thanks very much for coming along tonight again, and we'll see you again at either the next webinar or at the March section meeting, which is planned to be held on the I've forgotten what the date is. I think 23rd of March, 22nd of March, something like that, in Goosetree, hosted by the Macclesfield Astronomical Society. So I'm planning to be there again. I'm assuming my flights don't get disrupted again, or travel arrangements, depending on how I decide to come down. And I'll hope to see many of you along at that meeting. So thanks for coming along tonight, and thanks very much for attending, and good night. And if it's clear where you are, I'm afraid the moon is still very bright, another so-called supermoon. So maybe you won't be getting your telescopes out for faint fuzzies tonight, but whatever you get up to, I hope to hear from you over the next few weeks. Thanks then, bye for now.